I don't know if you are like me, but I've been blown away by the various talks today. Some telling me about their epiphanies, about their journey across science, across motivating other people. So what I would like to do is I would like to explain my own journey into trying to understand the wonders of nature. I tend to work in a field of research every 10 years, and after that I get bored. So I've got attention deficiency, people might say. I've done optical computing, I've done microsystems, and I've been blown away 5 years ago by a talk given by Julian Vincent about nature. And what I would like to do is I would like to convey some of the wonders of nature and how nature is actually very smart. We are talking about transition. This is a theme of this session, transition. And things are moving fast, very, very fast. In 1980, the deposit of cryoliths disappeared in Greenland. You might not have noticed that. Cryolith is basically used for the processing of aluminum. And artificial cryolith has been designed and created. Terbium, 2012, the natural deposit of terbium have disappeared. It is slightly more annoying because this was used in order to do light bulbs, high-efficiency light bulbs. Hafnium. When I talk to my students and I talk about hafnium, people say, God bless me. Hafnium in 2018 will disappear. This is more problematic. Hafnium is being used in order to reduce by 40% the consumption of electricity in your electronic circuits. Within a period of 100 years, most of the common metal will not be easily taken out of the earth. So we have to do something about it. What can we do? We have lived in a period where we heat, we treat, and we beat material. If you look at the evolution of society, the transformation of tools from stone to copper, bronze, and iron has been dictated by the mastery of fire, the ever-increasing control of the temperature of fire. And that has continued with silicium. We are at the age of microelectronics, where you need temperature over 1,500 degrees in order to be able to rarefy the different materials you want to use. But nature doesn't do that. Nature works at constant ambient temperature, ambient pressure. So what are we doing wrong here? If you look at the most common natural element you find in the planet and the Earth crust, the living world uses only one of these common elements compared to the others, oxygen. The living world uses carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, in order to be able to create these organic molecules, these amino acids, these proteins, and these cells, which are the basic building block of life. And all that, I repeat, at ambient temperature, ambient pressure. So can we learn about that? The fact that nature uses a limited palette of materials, 20 materials, roughly. Nature is a craftsman. Look at this beauty. This is a diatom. You have 100,000 species of diatom, unicellular algae you can find in the living world. On the right-hand side, you have coccoliths. You will find that in the White Cliffs of Dover. Look at the beauty, the symmetry that these elements achieve. They are beautiful, but they are also very useful for mankind. The diatoms are being used to purify water at very low cost. They are being used as gas sensor. People have been able to extract the protein which create this beautiful symmetry of holes in order to increase the diffraction efficiency of gratings. People start trying to learn from nature. How can we learn in a more systematic way what nature can provide? Now, Michael Ashby created what we call Ashby plot, which allows to draw very quickly specific properties, in that particular case, mechanical properties of elements. And if you look very carefully at the different elements you find in the living world, you will see that they match, they overlap our existing man-made products. This material can have the same performance as man-made products. So that's very useful. Sometimes they can work even better than man-made products. So how do they do that? What is the secret behind it? There's a first secret, which is what we call the rule of mixture. And this is where one of the wonders comes along. You can have very two weak material, brittle material. When you put them together, you create a very tough one or a very strong one. This is very counterintuitive, isn't it? This is an example when you take collagen and hydroxyapatite, and you end up with bone, which has higher fracture toughness than the two elements taken individually. Nature uses this interplay between universality and diversity. If you look at the top, you start with basic building blocks. And there are many building blocks you can make out of all these atoms I've explained before. So you have a diversity of choice. But the way you assemble them can be quite universal. It can be in the form of an helix. It can be a form of laminated layers, taken one on top of another. And you end up creating a variety of material, like bone, like cornea, like tendon, like plant stem, like leaves, which create very different functions. So you see, nature does use universality and diversity in order to create these different materials. The key is to get those materials at a given scale for a very specific function. What nature does, and we are very poor at doing, is using the material and building inherent hierarchical functionalities. And you find that in the case of the bone, or in the case of the bamboo, where you can have up to 7 different layers of functionalities. And you can mask the individual drawbacks of elements by using these different hierarchical functions. We don't do that. We do not know how to do that. We tend to use modular, like a Lego type assembly. Nature is much smarter than that. And it's this golden triangle. Looking from the bottom up, you start with a material building block you are using. And it is a combination where process, which is manufacturing process, structure, lamination, helix, dictates the properties and obey the functional requirement. This building block will form the basic element of the next building block. Higher is the functionality scale, functionality ladder. And every single time you also look at sensing whether or not the basic elements still obey the function. This is another importance of nature, is a dynamic effect that elements of nature have. Nature, for billions of years, have known how to self-heal, how to change resources. A deer, for example, during the mating season, will draw the calcium from the bones and put that on the antlers because it will be the time to fight, or the suitors for the females. Once the mating season has stopped, the calcium go back to the bone. Reallocation of resources in dynamic times is also very important. What is very important in nature is the information that is inherent in all this level of functionality. We do not do that very well in our man-made products. Nature does it beautifully. Therefore, we need to have a holistic design. We need to be able to take into account what nature offers us and try to design it to get the maximum or the optimum functionality. Another lesson that nature gave us is that the solutions they have are just good enough. Remember that joke about the two people hunting and they are pursued by a bear? And one hunter said to the other, I just don't need to be very fast, I just need to be faster than you. Nature just needs to be good enough for these living elements to survive. But it has to do it faced with a multiple series of constraints and for multiple objectives. So what we call in engineering is a multi-objective, multi-element, nonlinear optimization design. Quite a long word for it, but this is what nature does all the time, and we can learn a lot on how to be able to do that. We have now the tools, the mathematical tools, the computer tools, in order to be able to get the most robust design for what we want to do, or the most optimum design, not necessarily maximizing the design, making it optimum for what we want. We have also to work against our intuition. For example, if you want to go very fast, for a boat, for example, or a car, having a very, very smooth hull is not going to help you. This is where rough is actually better. Take the example of the eagle. Take the example of the owl. The owl has these serrations in the primary wing of the hull. They do it because they want to reduce the boundary layer. They're adopting a strategy of dividing and conquering. Instead of creating big vortices, big turbulence, they create very small ones, which allows them to go faster, but also to go in a very quiet manner to be able to attack the prey. This was used for the Speedo swimsuit, at the point where actually the Olympic Game Committee decided to ban such swimsuit, because the majority of the people wearing were winning Olympic gold. Another example, using control directionality of the layers allow you to create a material much stronger than each other layer taken individually. Making a material which is energy absorbing, you just put some holes in it in order to make it energy absorbing and much more impervious to impact. Very counterintuitive ideas. In conclusions, what I would like to be able to do is all these old lessons that nature has given us over the last 3.8 billion years, and be able to adapt them for new beginnings. And I want to be like Georges Mestral in 1942, as he was walking his dog in the Swiss Alps, and notice this bird of burdocks in the fur of animals. He spent 10 years to try to understand it, to try to replicate it. And what we have now is we have Velcro. 10 years in order to get a manufacturing process which allowed to replicate the essential idea of what the perk of burdock is. I am 5 years into that journey. I still have another 10 years to go in order to learn more about what nature can offer. But it's something at least I know, is that in the pursuit of nature wonders, we are all lifelong learning students. Thank you very much.